So our next speaker is Professor Chris Drovandi. So he's Professor of Statistics at QUT. He's also the Director of the Models and Algorithms Program at the QUT Centre for Data Science and is an Associate Investigator in ACEMS. So Chris is also going to talk about some of his work funded by the RSS.
So I'm going to be pretty ambitious today. I'm going to try and talk about 2 papers in 10 minutes. So these papers arose from the RSS funding. So the first paper is about efficient parameter estimation for intractable likelihood models. So this work started when I went to visit Scott Sisson at UNSW. So I used some of the funding to go visit Scott. And we made some good initial progress on the project. And then eventually my master's student, Jacob, took over the project, did some really great work on it and turned it into a really nice paper. And this is also in collaboration with David Fraser from Monash. Okay, so Bayesian statistics, we're interested in sampling from the posterior distribution. So the posterior is proportional to the likelihood times the prior. Now, in standard Bayesian algorithms, we would need to be able to evaluate this likelihood function pointwise as a function of a parameter. But unfortunately, for very complex models, it's not feasible to get a tractable expression for the likelihood. But in many cases, it's possible to generate simulations according to the model. So the question becomes, can we do parameter estimation without having to compute the likelihood function and just being able to generate simulations according to the model? So a particular method that my group and collaborators have been working on is a method called synthetic likelihood. So with the synthetic likelihood, what we do is we take our full data set and we firstly reduce it down to a set of summary statistics. And then we make the assumption that the model summary statistic has a multivariate normal distribution with a mean vector given by mu and a covariance matrix given by sigma. And we allow this to potentially depend on the parameter of interest. And then what we do is we evaluate that multivariate normal density at the observed value of the summary statistic. So this becomes our approximation to the likelihood, and then we can just feed this into our Bayesian algorithm in order to sample from the approximate posterior. Now, unfortunately, we're typically not going to know what the relationship is between this mean vector and covariance matrix and the parameter of interest. However, we can estimate them via simulation. So we just propose some theta value in our Bayesian algorithm, and then we generate n IID data sets from our statistical model. And for each of those data sets, we compute the corresponding summary statistic. And then from that, we compute the sample mean and the sample covariance of those summary statistics. And then we just go ahead and we plug these straight into the multivariate normal density. And this becomes the approximation of the likelihood. Now, the problem is that if we're dealing with a high-dimensional summary statistic, which is something that we might want to do, it's very difficult to get a good estimate of this covariance matrix. So we're going to have to generate a large number of simulations in order to get a good approximation of that covariance matrix. And this is going to make the overall process very computationally intensive. So one approach that we've previously used in order to try to address this issue is that instead of using the sample covariance matrix, we use a shrinkage estimator for the covariance. So for this one, what we do is we shrink down the correlations and we leave the variances the same. Now, this approach works really well if there's not much correlation between our summary statistics. But if there is significant correlation between the summaries, then the shrinkage estimator doesn't work particularly well. And this can lead to poor approximations of the posterior distribution. So the approach that we came up with to try to overcome this problem is something called whitening BSL. And so what we basically do, it's relatively straightforward, is that we simply just transform our summary statistics by using this so-called whitening matrix. So if we choose this matrix in a particular way, the covariance of the summary statistics actually becomes the identity matrix. So we've effectively decorrelated the summary statistics. And so then what we can do is we can apply a very heavy shrinkage in order to reduce the number of model simulations that we have to do, but then also not affect the approximation too badly. Okay, so now just some results on this simple moving average example. So we've got two parameters here. We've got a data set of size 200, and we're taking our summary statistic to be the full data set. So here our summary statistic is 200 dimensional, which is very large for likelihood-free methods. So here's some results that we get. Now, because this example is so simple, we can actually compute the true posterior. So the first one over here is using the shrinkage estimator. So we're not doing much shrinkage here. So this means that we need to have a large number of model simulations. So for each estimate of the synthetic likelihood, we have to generate 5,000 simulations according to our statistical model. And we can see that it's not a bad approximation of the posterior, but there's definitely some approximation there. And then in contrast, when we go to our whitening method, which is this one over here, we can see that with the same number of model simulations, that we've actually managed to get a pretty good approximation of the posterior. But here, what we really want to do is we want to massively reduce the number of model simulations that we do. And so in order to reduce the number of model simulations, we need to be much more heavy with the shrinkage. So down here now we are setting the shrinkage to be 0. So we're effectively estimating the covariance to just be a diagonal matrix. Now, if we just do the standard kind of shrinkage approach, then we get this horrible approximation of the posterior. I mean, it's not even close at all to the actual posterior. Whereas when we go to the whitening approach, we actually still get a good approximation of the posterior, but we notice that we've been able to massively reduce the number of model simulations that we've had to do. Okay, so that was the first project. How'd they go with that? It wasn't too bad. Was that 5 minutes? So hopefully that was around 5 minutes. So, so for part 2, this one is about accelerating Bayesian computation via parallel computing. So the RSS funding allowed us to hire David Warren as a research assistant, who's this really incredible postdoctoral fellow who's now in the Centre for Data Science at QUT. And this was also in collaboration with Scott. So there's many applications in Bayesian statistics that we can accelerate by using parallel computing. So the ones that we looked at in this paper were approximate Bayesian computation, which is actually another likelihood-free method. So what we can do with this one is we can generate all of our model simulations in parallel. Another possible application is sequential Monte Carlo. So the idea of SMC is that we traverse a set of particles through a sequence of distributions that take us from the prior to the posterior. Now, the good thing about SMC is that we can do a lot of the computations independently on each of those particles. And the third application that we looked at was determining weakly informative priors for Bayesian inference. And so for this one, what we actually have to do is compute the posterior distribution many, many times for lots of different data sets from the prior predictive distribution. So most of the literature on accelerating Bayesian computation is focused on GPUs. But unfortunately, I'm not sure how many people have tried GPU coding, but it's not very easy to do. So it's not particularly easy for practitioners to be able to use. So what we focused on in this paper was actually using parallelization within CPUs in order to speed up the computation without having to do much change to the original code. So in particular, what we can do with CPUs these days is that they're capable of doing multiple calculations in parallel just on a single core. And so that was the focus on, how much can we speed up these things by taking advantage of this vectorization within CPUs. So we're going to look at an example involving simulating from a statistical model. So this is the naive R code. So this doesn't do any vectorization or parallelization. So this is sort of just a naive implementation. This is the same code, but vectorizing it. So we actually don't need to do this for loop over the number of cells. So we can actually vectorize that. So that's the vectorized R code. So this is code that would probably be written by a statistician. So a statistician would probably write code that's quite similar to this. And this one down here is the vectorized C code. So taking the same code, implementing it in C++. Now, the good thing here is that in order to take advantage of the vectorization, we don't have to make hardly any modification to the code. So all we have to do to exploit vectorization is that we just include this pragma statement. And so this is much more simple than taking this code and trying to write it, for example, in CUDA or something, or on a GPU. Okay, so what we did was we generated from this simulator around 8,000 times. So what we can do is that we can do these simulations in parallel with multiple cores, but then within each particular core, we can use vectorization in order to speed up the simulation. So we found that with the vectorized R code and using 16 cores to do this in parallel, and then vectorization within each core, is that we get a 430 times speed up compared to the original naive R code. So the take-home message is if you're writing your code in R or MATLAB, then of course you should vectorize the code as much as you can. Now, when we implemented it in C, and we used the 16 cores to do these simulations in parallel, but we didn't do any vectorization, we got a 1,000 times speed up. But then when we also incorporated that vectorization, we managed to get a further 4 times speed up. And so we basically get this speed up for free. All we had to do was add that single pragma statement to the thing, and then, you know, bang, you get a 4 times extra speed up. Okay, so let's just summarize the main outcomes of the funding. So I guess probably the best thing from the funding is that it was great opportunities for Jacob and also David Warren. So they got some training, and they also got the opportunity to develop some new collaborations. Another outcome is the strengthening of the collaboration between the nodes of ACEMS, so involving myself, Scott Sisson, and David Fraser. Hopefully we can get 2 Q1 publications out of this work. So it's looking very promising, but of course it just takes forever to get something published. I think we finished this work like a year ago now, but we're still in the process of trying to get it published. And because of this new collaboration now, we've been able to come up with more ideas that should lead to papers in the future. Okay, so that's it. So these are the 2 papers arising from the work I spoke about today. And thanks very much, ACEMS, for the funding. So it's obviously been very beneficial for myself and also for other people involved in the project. And I hope that ACEMS has managed to gain some benefit out of these outcomes. So thanks very much.
Thanks, Chris. There was a quick question in the chat from Peter Ballard. So he asked, do you know why the speed up was more than the number of parallel cores?
Yeah, so it's because of the vectorization. So if you didn't do any vectorization here, then the speed up would only be about 16 times. So it's the vectorization that really helps the speed up for this one. Okay, cool. Thank you. All right. Thank you again to Chris and Matthias. So I'm now going to hand over to Stephen Woodcock, who's going to chair the next session.
So the next 2 talks are related to the Industry Collaboration Support Scheme, which exists to provide financial support to investigators to work with external organisations, whether that's existing ACEMS partners or also potentially new partners. 2 talks in this session. The first one of which is Dan Cook, who is talking about working with data from the recent bushfire season, the 10-12 months ago bushfire season, and using the available data to look at testing some of the hypotheses that have been put out there as the potential causes or the origins of this. So without further ado, I'll just hand over to Diane.
So I just want to say this is joint work with Wei Hao, Cheng, and Emily from AT&T, and I think they're all on the call. So just some background to this. This work started with a visit by Emily in February, and our goal was to work on spatiotemporal visualization and analysis of emergency call data. But because that data is private, we needed to have some data that is sort of similar to that, that would be, that we could talk about more generally. And at that time of year, the bushfires were primarily in our minds before COVID. And some of the structure in what we're seeing in bushfire data is similar to what the emergency call data that Emily was working with at AT&T is like. So that's the motivation, but we've moved on to doing a lot of work on the bushfire data. And primarily this is Weihao's honours thesis. He's got another couple of days to submit his thesis, and also Chang's master's thesis, who started just this semester. So along with bushfires, there at the time in February, January and February, and even March, there was a lot of debate in social media about the cause of the terrible bushfires this last season. And you would have seen tweets like this saying it's an arson emergency, and then also a lot of commentary on the climate in Australia is getting hotter and drier, and we're more susceptible to lightning-induced fires. So another key part of this work is the availability of remotely sensed data, particularly hotspot data. This is a fairly new product. And back in January and early February, Grant Williamson posted a code to in a GIST post on how to access the hotspot data using R. And so this was kind of the background to getting started, because if we can have remotely sensed data, then we can maybe do some more automation in terms of detecting. So this is the hotspot data for October through March of the 2019 to 2020 season. A hotspot could be a bushfire, or maybe just sort of heat radiating from the surface. There's some quality control, so just the points measured, plotted here are ones where fairly reliably are fire data, fire hotspots. So along with that remotely sensed data, there's also data on historical fire origins from the Department of Environment, Land, Water and Planning, dating back to 2000 and prior to the 2019 fire season. We also have open data on wind speed, temperature, rainfall, fuel layers, road maps, so we can get proximity to nearest roads, fire stations, recreation sites. So all of that open data has been merged in order to make some predictions, to make a model for predicting cause, and also to predict the 2019-2020 season. So taking the hotspot data, we need to do some cluster analysis to determine ignition point. And then from the historical fire origins data, we have causes of fires that have been actually investigated. We combine all the supplementary data to both those data sets, build a training model from the historical data in order to predict the 2019-2020 season. Just a short overview of the clustering. So in order to do clustering of this data, of the hotspot data, we're going to do spatiotemporal clustering. That means we break the data up into hours, small hour chunks, and any hotspots, so this should say hour one hotspots actually, any hotspots in hour one will be clustered, and we use a general radius of 3 kilometers for the spatial clustering, because 3 kilometers is a reasonably well reported distance for fires not jumping from one place to another. We did a bit of experiment on that as well, but basically clustering spatially, that hotspots within a spatial radius are grouped together in a cluster, and then that gets merged to the next hour's hotspot data. We match that up to existing cluster centroids, and any that don't belong in those existing clusters form new ones. So on the basis of that clustering, we've taken the 76,000 hotspot points and reduced it to 1,000 ignition sites. And these orange dots in here correspond to those ignition sites that we've labeled based on the clustering. Now that looks like a lot of ignitions, but actually 1,000 ignitions, bushfire ignitions, is pretty common and is similar to the 2018 season. But you can see the breakdown over the years, over the months as well. You see that December was really a time that there were a lot of fires in the eastern side, and January as well on the eastern side. And then we had a bit of a hiatus in February when Emily was here, which is lovely. But it picked up again, particularly west of Melbourne. There were some more fires around the Colac area, I think. So just in terms of historical data, there's something like 8,000 points in historical data. Most of those are reported to be lightning starts. And about, quite a few are still arson and accident. In the right-hand side plot here, we've got this broken down by year. And so horizontally, we have the year for the different groups. The grey indicates over all the years, so just total number of fires. One curious thing to look at here, see if I can get annotate working. One curious thing to look at here is the accidents. In recent years, the proportion of fires reported to be caused by accident is sort of suspiciously increasing. We don't really know why that change in the reporting has occurred. Okay, so that was, so yeah, in terms of spatial origin of those different causes, lightning tends to be more concentrated in the eastern part of the state, accident in the middle, arson seems to be a couple of hotspots for arson around the state, and then burning off. So there's a different sort of geographic location for those. There's also now, if we can, with the combined data, if we look at distance to roads, one thing to notice here is that generally lightning start fires tend to be a little bit further away from roads than the other types of fire starts. So from that training data, from the historical data, we basically fit a random forest model. It slightly outperformed other models in terms of predicting the cause given a location of a fire. If we look at the model performance, I think I'm going to run out of time really fast. So I just want to point out a couple of things. Generally, the model is very accurate in terms of predicting lightning starts and also accidents. Slightly less, so arson starts tends to be confused with all the other sources, although it's pretty accurate. It's not too bad. And burning off burning off and arson are a little bit more difficult to distinguish completely from accident and lightning. There's also, we used a system called Local Interpretable Model Agnostic Explanations called LIME to do a variable interpretation. So which of those many different variables that were used are more likely to be associated with the different causes. This is a bit hard to digest, but basically some of what you expect, that the further away from roads, it's more likely to be lightning, closer to camping sites, and also wind effects. Then closer to camping sites and closer to CFA stations, a little suspiciously, then it's more likely to be arson. So in terms of now using that model to predict the 2019-2020 season, these are our predictions for the 2019-2020 season. So most of the fires were predicted to be lightning starts. In terms of arson, arson fires tend to be closer to the city, closer to the middle of the state. So we have these cause predictions for each of the 2019-2020 season. And just digesting that a little bit more, these are the over the months, and you'll see that predictions for burning off cause primarily is in October and something in December. Basically, this is a good indication that the model is working quite well, that burning off is predicted to be prior to the fire restriction season. And most of the fires are predicted to have been caused by lightning for that season. So just wrapping up, yeah, we have some policy implications, I think, to recommend that really, if we're concerned about the fires into the future, we may need to strategically place more sea base stations in closer to some of the less accessible regions to be getting on top of the lightning ignited bushfires. The CFA should really be asked about increasing number of accident caused fires in recent years, whether that's a policy or coding change, or whether that's substantially more careless campers or logging operations. And really the end result is that arson was really a very small source of fires, and maybe a sensor network for those closer to populated areas could be a recommendation. So just in terms of where this might be used for helping people in the field, we have a Shiny app developed that's still in progress. You can actually look at the link on here to go to this app to play with it. But here's the historical data. These are the causes associated with historical fires. If we click on a point in here, we get more information about that point. I'm not sure if this will come up. Yeah, so we can look at what at that particular location where the rain, what was the rainfall in previous year, what were the temperatures, some of the other variables leading up to that fire. These are the predictions for the 2019-2020 season. I think there's one curious little point in here. Let's put this on. Some of you might remember the fire on French Island, where there's a huge koala population in January. We're predicting that that fire was an arson start. And then there's also a fire risk map that we've developed. And this is, if we look at burning off, I think is the easy one. So burning off is really a big risk in the October season, but if you change from across the fire season, burning off, as we'd hope, we're predicting it's not a problem later on in the season. So that's all I want to talk about. Just a summary, we've got an algorithm to detect bushfire ignition from hotspot data. We've got a fairly accurate model, I think, in terms of generating causes. We've got quite a complete and adaptable workflow working with open data for hopefully this will be useful into the future. And we have a Shiny app to help communicate this. So that's all. If you want to look at the code for the analysis, Weihao's GitHub repo has that, and Chang's repo has the code for the app. And if you want to see these slides again, I forgot to mention there's this link here. So if you want to play with that Shiny app or get these links again, this bit.ly Vic bushfire ignition will get you to these pieces. So thanks for listening.
Thank you. Have we got time for a quick question again, or are we're running a little behind time? Or should we just move straight on to?
I do have a question.
Okay. Thank you.
Can I just?
Yeah, of course.
So, Di, I had did some work on bushfire ignitions in Victoria a few years ago, and what the sort of folklore at that time was that it was roughly a third between lightning, a third between human cause, and whether that was accident or arson, you know, was hard to distinguish. But a third of the fires were caused by electricity wires. And in fact, that was a big cause on Black Saturday. So how do electricity caused fires show up in your data?
So one thing that I didn't mention is in the historical data, there's actually 26 causes of fires. And some of those, so a lot of those smaller categories, I don't remember electricity being a main one, but there were a lot of small things like smoke, stack, spark or something that we combined.
Electricity was not a small one. Certainly it wasn't a small one on Black Saturday.
Electricity caused?
Yeah, a lot of them were, and there was a lot of money spent on trying to do something about power lines going through forests.
Yeah, so maybe we need to look at that one again, because I'm not sure where it pops up in the causes. The key ones were lightning and accident, and arson and burning off. And we actually had we put everything into an other category, but we didn't use the other category for our model predictions because it's you know, there's all sorts of things mashed into that other category.
I mean, the thing about electricity is that it's sort of localized along the lines. So, you know, you've got this sort of 1D spatial manifold where they happen. I know it's a big thing.
Yeah. Yeah. So all of this started from Emily's visit in February. It's been a lot of fun, actually.
I think the suggestion of carrying on some of these questions in the chats probably where we're going to have to go for time reasons. We've got Paul's talk to squeeze in now. Thank you, Diane. So Paul Wu, the QUT, is going to be talking about his work jointly with Swimming Australia Limited and the Queensland Academy of Sports, discussing basic methodologies, turning those into gold medals. So thank you, Paul.
Hello everyone, so my name is Paul and today I'd like to share a bit about what we did with the ACEMS ICSS grant we got to help grow this program research. So this was done with myself, Kerry and Chris, who you've heard from, some students, Lawrence, Michael and Alan, and a whole bunch of industry partners. So let's talk a bit about this. So it was to support this new program. So primarily it was to support a new relationship with Swimming Australia Limited. And it was also with the Queensland Academy of Sport. And we worked with the joint postdoc. And so this happened roughly mid last year to early this year. And so we had 3 targeted areas of investigation. One was about swimming relays and the analysis of those races, about prediction of winning times for Olympic swimming events and world championships, and then some preliminary work on pacing strategies within a race. So I'll focus today on the first 2. So the question was, how fast is good enough to win gold, to get a medal, or to qualify for the finals, right? And of course, if you ask our swimming partners, they say, actually, gold is what matters. Everything else is secondary. So about predicting winning times using past race results. So to start with, we did some Gaussian mixture models to identify trends in winning times. And so you can see early in the 1900s, there was much more improvement because you went from dedicated, more amateur athletes to more and more dedicated training programs and more professional. So this kind of finding of years with similar rates of improvement, and then doing some time series regression fitted with MCMC, here just showing from the late 80s to today, first place, third place, and qualifying times. For example, here for the men's 50-meter freestyle, and you can see it's getting very, very fast, but it's also very, very competitive. So the simplest approach, of course, is to use last year's winning time. But with this time series regression, with the autoregressive and moving average terms, not only can we outperform that, but we can also capture the uncertainty. And more importantly, look at things like what's the probability of winning. So mean error rate of 0.5% roughly, and 90% improvement compared to the naive approach. Some interesting findings was that the Olympics are on average about 0.5% faster than World Championships. So they are the premier event. And then the so what aspect. Okay, so as I say, all models are wrong, but some are useful. So here the main thing is actually looking at, well, what are the chances of winning? And that's something that's, of course, everyone's familiar with. Is a key advantage of the Bayesian approach. So for example, there's a 13% chance that the 2021 Olympic women's 100-meter backstroke will be faster than the world record of 57.57 seconds. So smallest chance, but there's a 73% chance though, that will be faster than the 2016 Olympics winning time of 58.45 seconds. So it's these kinds of analysis and predictions that our partners are interested in basically the coaches and the athletes to see, well, what are my chances of winning? Conversely, there's a 27% chance of winning time if you swim 58.45 seconds next year at the Tokyo Olympics. Of course, when you look at these times, I go, wow, they are fast. My swimming is much, much slower than that. So, of course, not only do we have the prediction, but we also have the prediction interval. And what we found was if there's a trend, the model does quite well, but it also picks up when there's quite a extreme occurrence. So for example, in the 2019 World Championships for the men's 100 meter, Caleb Dressel, he actually almost broke the world record. The world record that was set during 2009 when they had the super suits. So the super suits allowed swimmers to go much faster, less resistance, and was promptly banned shortly afterwards. So to be able to capture this in the future, we're looking into things like career trajectory modeling. So modeling swimmers and the individual race times over their career to see how they are progressing. This model was based off previous event results. Right, so that was about winning times prediction. And now I'll talk briefly about relay analysis. So relay is actually one of the premier events for Australia. Actually, many medaling opportunities. Well, swimming as well, of course, generally. So analysis, prediction of relay team makeup, right? Who do I select for my team? Strategies primarily around the order of swimmers. Do you put your best swimmers first, last, or do you bookend the race with them? And the impact on race outcomes. So we did fairly standard statistical approaches of linear regression and random forests, machine learning for prediction. So here I'm showing just some interesting things maybe, that the fourth ranked swimmer, so basically the worst swimmer in the team, usually tends to step up. So here I'm showing on the x-axis the relay time effect, and here we have the different covariates. So relative to the individual swim, they tend to swim faster. Also, that the USA tends to swim faster in the relay than in the individual. So there's something that they're doing. There's something in the water there that allows them to do this. Okay. So that's one aspect, is analyzing things that contribute to how fast people swim in the relay. I talked about the ranking within the team. I guess a bit of peer pressure here as well, the nations, and also the the pacing profile. But I won't dwell on the details of that. And then the other side was, well, how can we, using the random forest model, predict, given a particular team makeup and particular competitors in the race, what is the probability of gold, silver, bronze, or non-medalling? And so in our cross-validation, we found that our gold prediction had, bear in mind, this is only 20 data points, 100% sensitivity. And also it was very good at predicting non-medalling. So 93% of the time we predicted that correctly. But the challenging part is predicting silver and bronze. That's much harder. But luckily, the more focus from a practical perspective is gold and medalling or not. And so what were some of the most important factors affecting your result? One is the differential time. So that is based on the theoretical time. So the individual swimmers' season's best times for each team. What is the difference between your team and the best team in that race? The team average ranking, the best ranking. So all of those, the three most informational variables are about how strong your team is, right? The next variable is then starting to talk about strategy. So probably unsurprisingly, if your team is not very strong, you don't have a chance. But if your team is strong enough, then strategy can help get you over the line. And so that's where auto swimmers comes into play. And so how might this be used? For example, this was used in the 2019 World Championships for Canada, who they actually came in third place. And on the top, we've got the probability of gold, silver, bronze, or no medal. On the left, we've got different ordering strategies. Do I put my best swimmers, the first best and the second fastest, at the beginning and end, or at the beginning, a different strategy, or all these other strategies? So the strategy then went with actually was maximize their probability for bronze. And that's what they got. But you can see you could potentially make trade-offs. Okay, can I try to increase my chance for a silver, but also that increases my chance that I get no medal too. So it's kind of this decision support system. What are some of the outcomes of this? No, anyway, so we developed this winning times dashboard so that coaches and athletes can more easily get predictions and look at, there we go, get predictions of the race times and also look at the uncertainties. And so that's very important in terms of having the practical output. And of course, it means that we got to engage, go to the national trials for the world championships and so on, which was very exciting. So what are the outcomes of this? So we've got 2 applied stats papers, but probably more exciting going forwards is that it did help grow a program of research here that through our work with Swimming Australia, QAS, now there's more projects. Triathlon Australia and QAS are interested in agent-based modeling and possibly ABC. So that's a commercial research project. There's an honors project for energy systems and kind of hidden Markov models with the Australian Institute of Sport. So that's a new partner. I've got a subsequent injury, a commercial research project. So this is with AIS and the West Coast Eagles. So I've got a paper there on predicting injury risk with Bayesian survival models and time-varying effects, and another ICSS to support developing these new relationships here. And we're very excited about that because it involves not just the QUT node, but UNSW going forwards. And another thing is the strategic partnership under discussion with AIS, QAS, and high performance sports, kind of a 3-year program, 3 PhDs, and half-time industry research fellow. So yeah, just want to say a quick thank you to ACEMS that was enabled us to do this work and grow these relationships. There's a lot of exciting work coming up in the future, and to thank the students and the team, Kerry and Chris. Thank you.
Any questions in the chat? Still discussing. Any quick questions for Paul?
Hi, Stephen. I think there's a question from Jason White in the chat.
I lost it in the chat. Oh, yes.
There's one. Thank you.
Thank you. Paul, can you see Jason's question?
I can see
How influential
local factors. What makes a pool fast? I'm not quite sure what you mean by local factors here. Jason? Depending on where you go.
For bronze.
So this wasn't something that we at least explicitly looked at in the model. In theory, of course, there could be a, what do they call, a home court advantage. But this was not within this aspect of that particular investigation. But it certainly could be looked at further. I think it's more prevalent for team-based sports though, such as basketball and so on, where these effects have been investigated in the past.
Ron's question. Looking at personal bests versus performance at the Olympics, World Championships, and speculation that Australian athletes don't improve as much as, say, US swimmers. Can you comment on that?
Yeah, that's actually, so to quote our swimming partner, when they found, so the modeling results that the US tend to step up, verified actually some of their coaches' instincts and findings, and his conclusion was the bastards. So that is, so part of that actually is when they do national trials. So Australia has been doing trials further a couple months before the competitive event compared to the US, and we've actually changed that now. And so at the 2019 World Championship, that was only about a month before the races in Korea, South Korea, and Australia was quite successful, 4 out of 7 gold medals. Mark Lawrence's question, were the outputs made available to individual swimmers? So I went through, so QAS, they have a lot of physiologists who work with the athletes themselves and the coaches, and did all through Swimming Australia to Yako, the national coach. So that's kind of how the work propagated through.
Good. Thank you. We've got time for one last question. That's
Angelus? What position did the worst swimmer uplift their performance best? And then is there a possible project with psychologists as to why? Yeah, actually, so that is an area of interest. So why and some of that, of course, is the team environment. So there's, in the paper, we go into this a bit more about some of the psychological aspects, and more so because we are humans, right? We're social animals. So if we have a teammates who are doing really, really well, and I mean, there's pressure, right? You are the 4th ranked, that means, and you're the 4th rank out of 4 people. So there is that aspect of things. But then the question is, can we apply other techniques to help the other swimmers? Can the 1st rank, 2nd rank, 3rd rank, can they also step up more? So these are all psychology and the physical. That's what is needed to actually perform best.
okay. Can we just join me in thanking both Paul and Diane for the session? Thank you.